Here's a couple more graph problem examples. We've got this graph G4 shown here with 9 nodes and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 links, or 9 vertices and 11 edges. Consider the walk shown IFEA. Let's go ahead and draw it. We're going to start at I, F, E, A, B, E, H, D, B, E, H, D, G. And ends there. Okay, and this is a walk. It doesn't repeat any links, but it does repeat a node, node E. And the idea is that anytime you have a walk, you can find a path. Okay, and the general idea is that if you have a walk, let me draw sort of the general idea here. If you have a walk which is neither a path nor a trail, then it may repeat a node and a link. So for example, if I do this, okay, that is neither a path nor a trail because it repeats not only nodes but also links, or vertices but also links. And to turn that into a path, what we're going to do is we're going to, let me just use a green one, we're just going to go like that between the same two endpoints. Okay, we're just going to cut off that extra loop. Similarly, if I start with what is a trail, that looks like this, where I've repeated a node, I can turn that into a path by just cutting off that extra loop. And you can always do that. Okay, and so in this case here, for problem 11 shown here, I'm going to take this thing and I'm going to turn it into a path. Remember, paths are a subset of walks. Paths are a subset of trails, or a subset of walks. They're in alphabetical order there. And I'm going to just go like this. Okay, and there is a path that has the same two endpoints. I'm going to start with I, F, E, H, D, G. Okay, and basically you can always look at a walk, I, F, E, A, B, E, H, D, G, and look to see if there are any repeated nodes. And then what you can do is you can just take a chunk, including the repeated node and the stuff that's between the two repeated nodes, and cut it out to give yourself I, F, E, H, D, G. We know the E and H are connected. Okay, so we know we can go from this E to that H. We can just skip that part of the walk to end up with a path. And if our walk had multiple loops on it, we would do that once, and then we would look again to see if we had any more loops. So you might have lots of loops, okay, in which case you would have to cut them all off. Okay, you would just go like this. Okay, well, I hope that gets you the idea. Let's consider the next problem, number 12. Consider the graph G4 given above. Show that the sum of all degrees is equal to twice the number of vertices of this graph. Okay, now that I've drawn all over it, the degrees of the vertices and the vertices themselves, A, B, C, D, E, F, G, H, and I. And let's now draw out the degrees. A has degree 3. Basically, I'm going to make a little loop around A and see how many edges it crosses. 3. B is 3. C is, 1, 2, 3 for C also. Each loop counts as 2 to the adding up the degree of that vertice. D is 3. E is 1, 2, 3, 4. Highly connected. F is 2. G is 1. H, if I can draw it right here, is 2. And I is 1. And if I take the sum of the degrees, I get 3, 6, 9, 12, 16, 18, 19, 20, 22. And that's supposed to be twice the number of vertices. Size of the set of vertices is I meant to write edges here. Yeah, I'm supposed to be counting edges here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and so this is 1/2 the sum of all the degrees. And so that is a typo there. Okay, this is a general rule that you can follow, and it's very clear why this is true, because every edge counts as 2 when we count up the sum of the degrees of the vertices. Okay, as we count degrees of vertices, we count one side of each edge once. Okay, hope that helps.